Welcome to the first lecture of this week. So remember in the last lecture, we have seen a decomposition of Cn into some null spaces. Okay? And these null spaces, the powers of the matrices inside would be determined by the minimal polynomial powers, and the dimension of the null spaces would be determined by the characteristic polynomial powers. In this lecture, we are going to actually write the theorem corresponding to those results first. Right? Let us write the theorem. So I would first write here the decomposition that we have seen. Cn can be written as a direct sum of a minus lambda 1 identity to the power m1, this is null space, plus a minus lambda 2 identity to the power m2, and these continue until null space of a minus lambda k identity to the power mk. We have seen this type of decomposition, and let us try to make some connections. The minimal polynomial, the characteristic polynomial of this matrix and the minimal polynomial of this matrix would be important. The characteristic polynomial is s minus lambda 1 r1, s minus lambda 2 r2, going until s minus lambda k rk. Okay? So the characteristic polynomial powers are r1 to rk, and the minimal polynomial powers are s minus lambda 1 m1, s minus lambda 2 m2, going until s minus lambda k mk. Okay? And we see that here, these powers in these null spaces of these matrices would be determined by the minimal polynomial powers of the corresponding eigenvalues. Okay? Each of these null spaces would correspond to a single eigenvalue, single distinct eigenvalue. And we see that these powers are determined by the minimal polynomial powers here. What about the dimensions of these null spaces? We know that this null space has dimension R1, this null space has dimension R2, and this null space would have the dimension Rk. So the dimensions of these null spaces are then determined by the characteristic polynomial powers. Okay? And I know that here, the summation of these dimensions, R1, R2 going until Rk, the sum is equal to n. Why is that? Because I know that the characteristic polynomial should be an nth order polynomial if the size of the matrix is n by n. That means that these powers here, they should sum to n. Or I can look at this decomposition. I know that the dimensions of these subspaces in a direct sum should sum to n, the overall dimension of Cn. Okay? And I know that these minimal polynomial powers, on the other hand, should be somewhere between 1 and Ri. Okay? So this is the general information for the decomposition. Now we're going to look at what this decomposition can be used for. So here, Cn is decomposed into some subspaces. Do you think these subspaces are actually invariant? Are they invariant subspaces under A? The answer should be yes here, because these are nothing but null space of a polynomial of A. Null space of a polynomial of A. During studying the concept of invariance, we have seen that null space of any polynomial of A would be invariant under A. As a result, each of these subspaces are invariant under A. Okay? And when we can decompose Cn into the direct sum of some invariant subspaces, we know that we can use that decomposition to be able to obtain a simple representation for the matrix A. How do we do that? We find some basis vectors for each of these invariant subspaces, and we fill them into a P matrix, basis change matrix, and then we change the basis in both the domain and the codomain of A into that basis set that we find for Cn, and then the resulting A bar matrix, the simple representation would be block diagonal. And size of each block in that block diagonal representation would be determined by the dimensions of these invariant subspaces. And here, dimensions of the invariant subspaces are R1, R2 going until Rk. Therefore, by finding some basis vectors for these invariant subspaces, we can obtain a block diagonal representation for the matrix A, which would be whose blocks are actually having size Ri by Ri. Okay? Let us try to write this. So when we select, if we select P is equal to P1, P2, going until Pk, this is going to be my overall P matrix, basis change matrix, where Pi is composed of columns which are the basis vectors, for the subspace, null space of A minus lambda I identity to the power mi. Okay? Then we obtain A bar, which is equal to P inverse AP, and this A bar is going to be given as follows. It is going to be block diagonal because of the invariance of these subspaces, and these blocks A1 bar, A2 bar, etc. would be the blocks of that block diagonal matrix. And I would have zeros everywhere else. Okay? And we know that size of a I bar would be Ri by Ri. Okay? Why? Because in that decomposition, we know that when we obtain this block diagonal representation, when we obtain this block diagonal simple representation for the matrix, these block sizes would be determined by the size of the invariant, by the dimension of the invariant subspaces that we obtained our P matrix from. Okay? And the dimensions here are R1, R2 going until Rk. That means that this block is going to have size R1 by R1, R2 by R2, going until Rk by Rk. This is K, sorry. Okay? So we would have this type of block diagonal matrix. So here, if I look at this P matrix here, it is composed of K submatrices, P1, P2, Pk. And each of these submatrices should be composed of columns which are the basis vectors for the corresponding subspace. Okay? I know that the dimension of this subspace is Ri. That means that Pi should be composed of Ri columns. So this is composed of R1 column, R2 column, going until Rk columns. Okay? And when I sum the number of columns here, I would obtain n columns. And these are all columns here are in Cn. Okay? So this P is an invertible matrix. It's an n by n invertible matrix whose columns would form a basis for Cn. And these columns are coming from the basis sets of these individual invariant subspaces. Okay? And in that case, I can calculate our new representation after the basis change as P inverse AP. And in that case, the A bar would be block diagonal, where the size of each block is determined by the dimension of the corresponding subspace. Okay? So here the theorem is going to continue. Furthermore, Pi can be selected in a specific way such that these blocks, these sub-blocks AI bar has the following form. AI bar would be in the following form. Lambda I, going until the end. This is an Ri by Ri matrix. And on the main diagonal, I have the corresponding eigenvalue for the ith subspace. Below the main diagonal, I would have zeros. And above the main diagonal, I would have some element shown by stars here, or asterisk, and I would have zeros everywhere else. Okay? This last statement is saying something very important. These PI matrices, I can select these basis matrices in a specific way. So I can choose some specific basis vectors for these null spaces, such that each of these AI bars, the blocks of this matrix, would be in this form. Okay? And this is a very, very specific form, as you see, right? It is almost completely filled with zeros, except for the diagonal and the one above the main diagonal. Okay? And the diagonal is filled with the eigenvalues corresponding to the subspace that we are working with. Okay? Eigenvalues for the ith null space. And what about the main diagonal? I have some star elements, and these star elements are in this set. Star elements are either 0 or 1. Okay? I can find such a basis set for the ith null space that the resulting AI bar matrix here would be in this form, where the diagonal is filled with the eigenvalues and one above the main diagonal is filled with 0 or 1 elements, binary elements. Okay? So when I choose my PIs in this way for all of these subspaces, the resulting A bar, if PIs I from 1 to k are all selected in this specific way, the resulting A bar is called the Jordan canonical form. Of A. Okay? So when I select my basis vectors for all of the subspaces in this specific way, we are going to see what this specific way is in this course, in the coming lectures. But when I choose my PIs in this specific way, such that all of the blocks have this form, then the resulting A bar matrix is going to be called the Jordan canonical form of the matrix A. Okay? So let us try to understand what this really looks like. So I have A1, for example, can be in the following form. So this completes the theorem here. So we have seen that we can make such a decomposition, and this decomposition is going to enable us to find a simple representation for the matrix A, which is block diagonal, and even more, I will be able to select these basis vectors in such a specific way that each of these blocks are going to have this type of form. Okay? So I will, in this manner, I will try to find the simplest representation corresponding to the matrix A by using these invariant subspaces. Okay? For example, A1 bar can be looking like this, 3, 3, 3. A1 bar might be a 5 by 5 matrix when I select my basis vectors like this. And here, these elements can be 0 or 1. Okay? I just made this up. So let me fill in this matrix. It is really looking like this. So for example, this might be a candidate A1 bar. Okay? And you see that all of the main diagonal elements are filled with the eigenvalue 3, and below it I would have always zeros, and one above the main diagonal is filled with either 0 or 1. Okay? So you see that here I have this type of matrix. And sometimes what we do in this case is we try to group these ones into some blocks. Okay? So we try to group them into blocks like this. Okay? And we call these individual groups inside AI bar, A1 bar for example, as the Jordan blocks. Okay? Because these AI bars are forming the Jordan canonical form, then sub-blocks of A1 bar would be called Jordan blocks. And a Jordan block would be in the following form. It has lambda i's in all of the main diagonal elements. Below the main diagonal I would have zeros, and I would have always ones, one above the main diagonal. Okay? This is what a Jordan block would look like. So when I look at this one, this is not a 5 by 5 Jordan block because there are not always ones, one above the main diagonal. But I can divide this A1 bar into individual Jordan blocks. This is a 2 by 2 Jordan block. This is a 1 by 1 Jordan block. And this is a 2 by 2 Jordan block. Okay? So let me try to illustrate this a little bit more. So in this case, this A1 bar would still be in this form with the stars, either 0 or 1, and I can divide it into 3 Jordan blocks. 2 has size 2 by 2, and 1 has size 1 by 1. So when I look at these Jordan blocks, they would be in the following form. So I would have here, this is a 1 by 1 Jordan block. It doesn't have any ones. And this is a 2 by 2 Jordan block. It has eigenvalues on the main diagonal, and one above the main diagonal it is equal to 1. And this is a 3 by 3 Jordan block. Okay? And I have a 4 by 4 Jordan block like this. And I have a 5 by 5 Jordan block. Okay? These are all looking like Jordan blocks. This is 1 by 1, 2 by 2, 3 by 3, 4 by 4, and 5 by 5 Jordan blocks. Okay? Now let us consider a matrix. And here this matrix is going to have the characteristic polynomial given like this. S minus 2 to the 7, S minus 3 to the 3. Okay? And I will try to find, I will just make up a Jordan canonical form for this matrix. Okay? So I will have a 7 by 7, R1 is 7 and R2 is 3. So my simple representation A bar, and if this is Jordan canonical form, we're going to show it with J. Okay? This Jordan canonical form, A bar, which is going to be composed of that type of blocks, is going to have a 7 by 7 block for the eigenvalue 2 because of this power here, and a 3 by 3 block for the eigenvalue 3. Okay? So this is going to be my A1 bar, and this is going to be my A2 bar. Okay? This is A1 bar. A1 bar is going to be in this structure. So let us write this, 2, 2, 2. I will have 7 eigenvalues which are equal to 2. And one above the main diagonal is either 1 or 0. Okay? So I would have just this type of 1 or zeros. Okay? And for the eigenvalue 3, I have a 2 bar. And a 2 bar is going to be a 3 by 3 matrix because of this one. And one above the main diagonal will either be 1 or 0. It can be both 1, really. It just changes how many Jordan blocks this matrix is composed of. Okay? I can put here 1, and this would be then 3 by 3 Jordan block. And if I put here 1 and 0, this would be a 2 by 2 Jordan block and 1 by 1 Jordan block. Okay? These Jordan blocks are determined by the structure of these null spaces. For each matrix, they can be different. So now this is my A1 bar. This is my A2 bar. Okay? And how many Jordan blocks A1 bar contains? So here, now I'm going to try to group A1 bar into its Jordan blocks. Okay, and for that I would look at the continuity of ones here. So I see that these ones continue for 3 consecutive times. So this is going to be my 4x4 Jordan block. Okay, and here you see that there is only a 2 which doesn't have any 1 above. This is going to be a 1x1 Jordan block. And here I have another 2x2 Jordan block. So once you see these blocks, a I bar, you need to be able to immediately divide it into some Jordan blocks like this, which contain all ones, one above the main diagonal. Okay? Jordan blocks are in this form. So this is Jordan blocks. Alright? So this A1 bar is composed of now 3 Jordan blocks. One is 4x4, and the other one is 2x2, and the third one is 1x1. Okay? And what about this A2 bar? In this case, it's composed of 2 Jordan blocks. One is 2x2 size, and the other one is 1x1 size. Okay? So this is a Jordan canonical form for a matrix which would have this type of characteristic polynomial. Obviously, for the same characteristic polynomial, there are infinitely many matrices having the same characteristic polynomial, and those matrices actually each might have a different Jordan canonical form. So for example, if I erase this one here and make it 0, then there would be one Jordan block with size 3x3, and I would have 2 Jordan blocks with size 1x1 for each one, and I would have another Jordan block with size 2x2. Okay? So in the coming parts of this course, we are actually going to learn how to find the Jordan canonical form corresponding to a single matrix. So we are going to be given the matrix A, and the matrix A, by this theorem, is going to have a Jordan canonical form. And we will see that, we will try to learn how to identify that Jordan canonical form. For example, we will be looking at the characteristic polynomial, we will be looking at the minimal polynomial, and we will be looking at some other properties related to the matrix. Then we are going to identify what the Jordan canonical form of that matrix would be. And then what we are going to do is that we are going to find the P matrix, the basis change matrix, which would put the matrix A into its Jordan canonical form. So we are going to ask the question, which matrix P would give me the Jordan canonical form as my A bar? Okay? We are going to ask what this P is. Okay? We are going to learn how to find P, and we are going to learn how to find J in the coming lectures. All right? The first thing that we are going to do is to find out what the Jordan canonical form of a matrix is. We are going to be given a matrix A, and we are going to ask the following question. What is the Jordan canonical form corresponding to this matrix? Or what is the Jordan canonical form of this matrix? Okay? Before finding the P matrix, which would convert a matrix into its Jordan canonical form, we will identify what the Jordan canonical form of the matrix would be. All right? So first we will find J, the Jordan canonical form, and then we will ask the question, what is the P matrix which would put this matrix into its Jordan canonical form? Okay? So the first thing that, in order to be able to understand about the Jordan canonical form, or how we can find Jordan canonical form, we need to concentrate on the structure of these subspaces. Okay? I'm going to be concentrating on the structure of these null spaces. And in order to be able to understand that, I will start with an example, which we have already seen. So let us say that A is this matrix, 1, 2, 2, 1, and I would have zeros here. Okay? Now we know that this matrix has the characteristic polynomial d of s minus 1, s minus 2 square. And in the last lecture we have found the minimal polynomial for this matrix as well, and it was the same as the characteristic polynomial. Okay? So I have the first eigenvalue 1, second eigenvalue is 2, and I have these characteristic and minimal polynomials. Now I will look at those null spaces. In this case I can of course write my decomposition. C3, because n is 3 here, C3 is null space of A minus lambda 1 identity to the power 1, okay, plus null space of A minus lambda 2 identity to the power 2. This is my decomposition, and the dimensions here are, dimension of this one is 1 and dimension of this one is 2. These are the characteristic polynomial powers. These are the minimal polynomial powers. Okay? So this is my decomposition for this matrix. Now I'm going to try to investigate the structure of these null spaces. Let us see how. I will look at the first matrix. A minus identity. This is, lambda 1 is 1, therefore this is A minus identity. The matrix A minus identity. And that matrix is, subtract 1 from the main diagonal, and I would obtain this. Okay? So now what about the null space of this matrix? So null space of A minus identity. This matrix has rank 2. That means that its null space is one-dimensional. Okay? As a result, this null space is going to be having a basis with only one non-zero vector. And in this case, one non-zero vector in the null space of this matrix would be 1, 0, 0, for example. Okay? So what is the dimension of this null space? Dimension of null space of A minus identity is just 1 here, because it has only a one non-zero vector inside the basis set. Okay? Now I'm going to ask the following question. What happens when I take the square of this matrix? A minus I square. Let us take the square of this matrix and look at the null space. The square of this matrix is going to be 0, 1, 0, and I would have 0, 2, 1. Square would be this matrix. And now I'm asking, what is the null space in this case? A minus identity square. Okay? And in this case, I would have the rank of the matrix is 2 again. So null space dimension is 1, and one vector inside the one non-zero vector inside the null space is 1, 0, 0. Okay? So you see that here, what is the dimension of the null space? A minus identity square. It is still 1. Okay? So what happens when I take the cubic power here? A minus identity cube, and this is going to be, just multiply these matrices and you would obtain in this case this matrix, and you would see that the null space of A minus identity cube is again span of 1, 0, 0, and the dimension of null space of A minus identity cube is still 1. Okay? So you see that here, you can increase the number of powers there, okay? So you can increase the power there, and you would still see the same null space, okay? So when I look at these null spaces, then I would have null space of A minus identity, or let me write lambda 1 identity here, because lambda 1 is 1, I can still use this. Lambda 1 identity, then when I take the square of this matrix, the null space does not change. A minus lambda 1 identity square null space of A minus lambda 1 identity cube, that is A minus identity cube, and the equalities would continue forever. Okay? So in this case, for the first null space of this matrix A minus lambda 1 identity, I start with an eigenspace. This is my eigenspace. And when I take the square cube of the matrix, really null spaces do not change at all. Okay? Nothing changes in the null space. So here, I'm going to be looking at the other null space as well. A minus lambda 2 identity. And that is related to the matrix A minus 2 identity. Okay? Let us calculate this matrix. I would have minus 1, 0, 0, 1 here. Is this matrix. What about the null space? Null space of A minus 2 identity would be one-dimensional, right? Because this matrix rank is 2, and therefore null space dimension is 1. I have span of and a single non-zero vector. A non-zero vector inside the null space of that matrix would be 0, 1, 0. Okay? What about the dimension of this null space? A minus 2 identity would be 1. Okay? Now I'm going to be taking the square of this matrix, and we'll be looking at the null space. A minus 2 identity square. Okay? Let me take the square of this matrix. So I have 1, 0, 0, 0, 0, 0, and 0, 0, 0. This is the square of that matrix. And now when I look at this matrix, I see that null space dimension is going to be 2. It increased by 1. And I would say here that the rank is 1, because there is only one linearly independent column here. Okay? So null space of A minus 2 identity square is here just span of 2 non-zero vectors, because the dimension is 2 now. Okay? And dimension of null space of A minus 2 identity square is 2 here. Null space dimension, when I take the square, it increased. Okay? And if I tell you 2 non-zero vectors in the null space of that matrix, you will see 1, 0, 0, and 0, 0, 1, 0, and 0, 0, 1. Okay? 1, 0, 0 is not in the null space, of course. Okay? So now I'm going to be looking at the cube. I hope you are not bored here. So let me take the cube, okay? A minus 2 identity cube. And now in order to be able to calculate this matrix, I will multiply these two matrices, okay? And then I will be looking at the null space. All right? So here, if I multiply this matrix with this one, I would obtain minus 1, 0, 0, and I would have 0, 0, 0 like this. Now, what about the dimension of the null space? It is going to be 2, and what is the null space? So in this case, null space of A minus 2 identity cube is going to be span of 2 non-zero vectors, all right? And these vectors would be again 0, 1, 0, 0, 0, 1. And what about the dimension? Dimension of null space of A minus 2 identity cube is equal to 2. Okay? So you see that when I take the square, the dimension first increased, and when I increase the power more to 3, in that case the dimension remained the same and the space remained the same. Okay? So this is always the behavior of these null spaces. They might first increase their dimension, but when you increase the power, but when you increase the power above some value, then the dimension no longer increases. and the space would remain the same. This is always the behavior of these type of null spaces. Okay? So these null spaces in this decomposition would always be behaving in this manner. So when I increase the power, sometimes they might increase their dimension and their basis vectors, but after some power here, they would stop growing and they would start being the same as the earlier null spaces. So now let us try to look at this second null space here. Okay? What about its behavior? So this was my D of S. I will erase this one. So I will just write here D of S is equal to M of S, S minus 1, S minus 2 squared. So now let us look at the other null space. Null space of A minus 2 identity, or I would write lambda 2 identity. Okay? This is this eigenspace that I have found here. All right? Now what happens when I take the square here? In that case, this null space dimension has grown. Okay? And the dimension has grown from 1 to 2. And what is the relationship between these two null spaces? So you see here that this null space, the basis vector of this null space, is also a basis vector of the second null space. Okay? So you see that this the first null space is a subset of the second null space. Okay? So you see that here, this null space becomes a subset of the null space, A minus lambda 2 identity square. Okay? And I know that these two null spaces are not equal. So in mathematics, we show this as the following. We put here a not equality sign. This means that this null space is a proper subset of this null space. Okay? So that means that this is the subset of this null space, but they are not equal. Okay? There are definitely extra vectors here which are not inside the smaller null space. Okay? We know that a set is always a subset of itself. Okay? And this is a proper subset sign. Okay? If I just write the subset relationship, then those two subspaces might be equal, because every set is a subset of itself. Okay? So here we are excluding the equality sign. That means that proper subset sign, this sign, is equivalent to the subset sign plus not equal sign. Okay? That means the proper subset relationship. So we see that this null space has grown by adding some extra vectors, and they are not definitely equal. So the first null space is a proper subset of the second null space. Okay? And what happened afterwards? So when we increased the power to 3, the null space remained exactly the same. All right? So we have exactly the same null space when I have A minus lambda 2 identity cube here. And what about taking the 4th power, 5th power, etc.? You try to continue this type of derivation, and you would see that when I increase this power further, the equalities are going to continue forever. The null space would not be able to grow anymore. All right? So you see that this null space started with the eigenspace, and it has strictly grown, and it remained the same. Okay? And what about the earlier one? The earlier one remained the same just from the start. Okay? Let us write the dimensions of these subspaces. In the earlier case, the dimension was 1, 1, 1. It remained all the same at each power. What about this one? The dimension was 1 here, dimension was 2, and dimension remains 2 forever. Okay? So when therefore, we are now going to write the general theorem for the structure of these matrices, these null spaces. Okay? We are going to see that these null spaces would always strictly grow or remain the same forever. Okay? When we increase these powers here on top of these null spaces, we would see that they would strictly grow or they would remain the same forever. Okay? And what about this one? This is remaining equal at each power. Because in this case, this equality is satisfied just from the first power increase. Okay? So since this equality is satisfied from the first power increase, all of the null spaces remain the same. Okay? So this null space is already the largest null space that you can reach. Therefore, when you increase the power here, no dimension increase happen. On the other hand, this eigenspace is not the largest null space that you can reach with this power 1. Okay? So when you increase the power, this null space grows, and at the second power it reaches the largest dimension it can reach. And then its dimension remains the same. Okay? So here, remember this decomposition. In this decomposition, this dimension is going to be important. Dimension 1 and dimension 2. And these powers would be important as well. Okay? These powers are going to determine from which power we're going to have the equality. Okay? So when I look at this power for the first null space, this power is 1. That means that this null space with the power 1 is going to be the largest null space that I can reach. And its dimension is going to be 1. And since this is the largest such null space I can reach, when I increase the power, no growing happens. Okay? So there is no growth here, because this power is 1, that is already the largest null space that I can reach in this form. Alright? And here, this power is 2, therefore the largest null space is reached at the power 2. And the largest dimension that we can reach is 2 here. Okay? So then, when I increase the power from 2 and on, then I won't observe any increase in the null space dimension. Okay? So again, we are going to have the important quantities. This power at which growing stops is always the minimal polynomial power of the same eigenvalue. Lambda 2 has the minimal polynomial power 2, so the dimension growth is going to stop at the power 2, and the dimension that we are going to reach would be equal to the characteristic polynomial power 2 again. Okay? And in this case, both of them are 1, and in this case, both of them are 2. So now let us try to write the theorem related to this. So this theorem is going to explain these null spaces in our decomposition. All right? So here I have the theorem. So in order not to write actually A minus lambda I identity, I will define here this matrix, sigma I. Okay? This is going to be defined as A minus lambda I identity. So this matrix here, A minus, if I is equal to 2, it is this matrix. If I is equal to 1, I have this matrix. Okay? So now I will try to explain the structural null space of sigma I square, sigma I cube, etc. Okay? So we say here in the statement null space of sigma I, then this is going to grow when I try to take the second power. Okay? And this growth is going to continue until this null space of sigma I to the power mi. Okay? And afterwards, everything is going to remain the same. There will be equality afterwards. Sigma I, mi plus 2. Equalities are going to continue always. Alright? So it is what we see here, and it was what we saw in the first null space case. In the first null space case, mi was 1. Okay? And in that case, this was the largest null space. So there were equalities. So mi was 1, so this was the same as this one, and there were equalities forever. Okay? Just from the start. And now I have seen this structure. And what about the dimensions? When I look at the dimensions of this null space, dimension of this null space, and dimension of this one, and the dimension of this one, this is a proper subset sign. That means that this null space is definitely bigger. It cannot be equal to this one. Therefore, the dimension of this one would be strictly larger than this one. Okay? And the dimension increase is going to continue like this until we reach the largest dimension possible. And then the dimensions are going to be equal forever. All right? And what about this largest dimension that we can reach here? That largest dimension is going to be, interestingly, just equal to Ri. Okay? Which we already said here. All right? So the largest null space is reached at the power equal to the minimal polynomial power, and the largest null space possible has a dimension equal to the characteristic polynomial power. Okay? So that is our main structural theorem for these null spaces. Okay? So now I will try to give some partial proofs for some parts of this theorem. Okay? So it is not really going to be difficult. So just you would have to know some basic facts, but let us try to explain some parts of this theorem using some proofs. Partial proof. So here in my proof, I won't be explaining why this is the power at which we reach the maximum null space, or I won't explain why this is the largest dimension that we can reach with these null spaces here, but instead I will try to explain these subset relationships. Okay, in my proof. So I will first show the following. First, we show that null space of sigma I to the L is always a subset of null space sigma I to the L plus 1. Okay? So really it doesn't matter. So when I increase this power, this null space should always grow or remain the same. Okay? So that is what subset relationship means. And this one is saying it grows and it is not the same. Okay? It is a subset, but it's not the same anymore. So let us try to prove that when I increase the power of the matrix inside the null space, the new null space is either larger or it is the same. Okay? So I need to prove a relationship like this. This is my null space of sigma I to the L plus 1. And the other one can be either equal or it is strictly smaller. Sigma I to the L. Okay? In order to be able to prove such a thing, I am going to take an arbitrary element in the first null space. And then I will show that it is inside the second null space as well. Okay? So let us say that let X be in sigma I to the L be arbitrary. It's an arbitrary element of this null space. What does that mean? In order to be able to show this relationship, I need to show that this X is also an element of the larger null space as well. Okay? The other null space. So if X is inside the null space, then I would have sigma I to the L times X is equal to 0. Okay? X is inside the null space of a matrix. That means that that matrix times X should be 0. So now I'm going to multiply both sides of this equation with the matrix sigma I. Alright? Sigma I times sigma I Lx is equal to sigma I times 0, which is still 0. Okay? But this means that sigma I to the L plus 1x is equal to 0. But this means that X is inside null space of sigma I to the L plus 1. Okay? So any X, any element of this first null space is also an element of the other null space. That means that this null space should be a subset of the other null space. But remember, the subset relationship means that this is either strictly smaller or equal than that one. Okay? So let us try to do the other proof. So maybe I should, no, I cannot write there. So I will erase this proof, unfortunately. So I will just write. This was the first part that I'm going to prove. And the second part is that when these null spaces start becoming equal, then they would remain equal forever. Okay? Part 2, we show that null space of if null space of sigma I to the L is equal to null space of sigma I to the L plus 1, then they would remain the same when I increase the power. Null space of sigma I to the L plus 1 is equal to null space of sigma I to the L plus 2. Okay? So now let us try to prove such thing. So we have already shown that we have always subset relationships here. Okay? Now we are trying to show that as soon as we have equality somewhere, then we are going to continue to have equalities. Okay? Suppose that we have equality at the Lth power between Lth and L plus first power. We are going to continue to have equalities forever in the next powers, or in the next powers, etc. Okay? So here let us try to do that. In this case, I need to, under this assumption, assume that null space of sigma I to the L is equal to null space of sigma I to the L plus 1. Okay? Suppose that I have an equality like this. I am assuming this, and then we need to prove that null space of sigma I to the L plus 1 is equal to null space of sigma I to the L plus 2. Okay? I need to prove this. So now this is a subspace equality. Okay? We know that we can actually prove subspace equalities in only a single way. So I need to show that null space of sigma I to the L plus 1 is a subset of null space of sigma I to the L plus 2 under this assumption, and I need to show the reverse subset relationship. So I need to show that this is also a subset of this one. Okay? Null space of sigma I to the L plus 1. Okay? If I can show that both of these subset relationships are equal under this assumption, then I am done. Okay? So in part 1, I have to show this subset relationship. But do I really have to show this? Because we have already seen in the first proof that I made that this type of subset relationship would always hold. When I increase the power, the null space either grows or remains the same. Okay? So I don't need to prove that. This is already proven. Okay? So I need to show that only that this subset relationship holds under this assumption. Null space of sigma I to the L is equal to the null space of sigma I to the L plus 1. So I need to show that this subset relationship holds. All right? So I'm going to take an arbitrary element in this null space. All right? Let X be an element of null space of sigma I to the L plus 2. Okay? I take an arbitrary element here and show that it is also an element of the null space on the right. So that means that sigma I to the L plus 2 times X is equal to 0. X is an arbitrary element in this null space, and then sigma I to the L plus 2, that matrix times X should be equal to 0. Okay? I'm going to separate this as follows. Sigma I to the L plus 1 times sigma I X. This is equal to 0. Okay? But this is the same equation. Sigma I to the L plus 1 times sigma I is sigma I to the L plus 2 times X is equal to 0. All right? So now this means that here, this vector sigma ix, when I multiply it with sigma I to the L plus 1, gives me 0. So that means that sigma ix is inside the null space of this matrix. Sigma ix is inside the null space of sigma I to the L plus 1. Okay? And what we are trying to show? We are trying to show that X is inside this null space. I assume that X is in this. I need to show that X is in this as well. Okay? Sigma ix is inside the null space of sigma I L plus 1. But I know that this null space of sigma I L plus 1 is equal to null space of sigma I to the L by the assumption. Okay? That means that sigma ix is an element of sigma I to the L as well, because these two null spaces are equal by the assumption. Okay? That means that sigma I to the L, sigma ix is equal to 0. If this vector is inside the null space of this, then when I multiply this matrix with this vector, then I would get the 0 vector. Okay? But this is going to give me sigma I to the L plus 1x is equal to 0. What does it mean? That means that x is inside the null space of sigma I to the L plus 1. Okay? And that completes the proof. Okay? So we have shown that here, these null spaces are always strictly growing or they're remaining the same. And we have shown that when they are equal at some power, then at some power increase, then they continue to be equal forever. Okay? So there are, of course, some parts of this theorem that I have not proven. For example, I have not proven why this dimension growth or the growth of the null space would stop at the minimal polynomial power. I haven't proven that, or I haven't proven why the largest dimension that we reach here at this power would be the characteristic polynomial power of the eigenvalue. Okay, so there are, of course, things that I did not prove, but I have almost completely proven the lower parts, except for this power mi. Okay. So now let us try to see the benefit of this theorem in an example. So our example is this. The A matrix is given as 1, 1, 1, 1. I would have zeros here, and I would have a 2. So I would have, I'm asking what is D of S and what is M of S. Okay. So let us first write D of S. So this is an upper triangular matrix. Actually, it's already in Jordan canonical form. And when I have an upper triangular matrix, the eigenvalues are the diagonal elements. Okay? So I see that there are 3 eigenvalues at 1, and there are 1 eigenvalue at 2. So the characteristic polynomial is S minus 1 cube and S minus 2. Okay? Now remember how in the earlier parts of this course how we found the minimal polynomial. Okay? In the earlier parts I have determined some alternatives for the minimal polynomial, and then I have substituted A into S, and I try to obtain zero matrix at the result. That is how I determined the minimal polynomial. But here we are going to use this null space properties in order to be able to determine the minimal polynomial. Okay? So here I can ask you, for this matrix, how many minimal polynomial possibilities do there exist? How many different minimal polynomials such a matrix can have? So I have this characteristic polynomial. For example, can M of S be S minus 1, S minus 2? According to the properties, so does this alternative does this alternative satisfy all of the properties of the minimal polynomial? Yes, this actually satisfies. All eigenvalues appear here, and the powers are between 1 and the characteristic polynomial powers here. What about this one? M of S, S minus 1 square, S minus 2. If I, of course, put square here, it won't satisfy the second property of the minimal polynomial. Then this polynomial would not divide the characteristic polynomial. So this power should always be 1. S minus 2 should always have power 1, but the other power can change. It can be 1, 2, or 3. Okay? So this is the second alternative. And the third alternative would be S minus 1 cube, S minus 2. Okay? In the third case, I have the equality between the minimal polynomial and the characteristic polynomial. Okay? So here, remember how we determined the minimal polynomial in the earlier instances. So what I did was, so let me say that this is M1, M2, and M3. I would first substitute M1 of A. This would be A minus identity and A minus 2 identity. And I will ask the question, is this equal to 0, 4 by 4? Okay? If this is equal to 0, then this would be the minimal polynomial. Then I would check this one. If this is not 0, I would check the second one, and then I would continue to the third one. Okay? Here, I don't want to proceed in this way. Okay? So instead, I will use these null space properties. All right? I know that when I look at the null space of the first eigenvalue, the first eigenvalue is 1, I will look at the null space dimensions. Okay? I will increase this power until I reach the dimension Ri, which is equal to 3. Okay? And the power that I reach dimension 3 would be my minimal polynomial power for the eigenvalue 1. Okay? So I will use this theorem in obtaining the power of the minimal polynomial for the eigenvalue 1. Okay? I will look at the dimensions of these null spaces, and I will determine the power here at which I reach the characteristic polynomial power as my dimension. The characteristic polynomial power is 3. So I will look at these null space dimensions, and I will actually try to find out the power at which I reach the dimension 3 for this null space. And that power is going to be my minimal polynomial power for the first eigenvalue. You see that it is only the power of the first eigenvalue which is unknown here. The other one should be definitely 1. Okay? So now let us try to do this. So I will look at the matrix sigma 1. Sigma 1 is equal to A minus lambda 1 identity. Okay? And lambda 1 is 1, so this is A minus identity. Okay? So in order to calculate A minus identity, I will subtract 1 from the main diagonal here. Let us subtract 1, 0, 0, 0, and I would have 1 here, and I would have another one, and I would have zeros everywhere else. So this is my matrix A minus identity, or sigma 1. Okay? So let me look at null space of sigma 1. What is the null space of the dimension of the null space of sigma 1? What is the rank of the matrix? If we can determine the rank, then by using the rank nullity theorem, we can determine the null space dimension, or the nullity of the nullity of the matrix. Okay? So here I see that the rank is 2 because I have 2 linearly independent columns here. Therefore, what should be the dimension of the null space of sigma 1? This is going to be equal to 2, okay? Because by the rank nullity theorem, summation of the rank and nullity should be in the number of columns, the dimension of the domain, which is the number of columns here, which is 4. So in this case, the rank is 2 linearly independent columns. That means that the null space dimension is going to be 2, because the sum should be 4, all right? So at this dimension, did we reach the largest dimension possible for the null space? If this was equal to the characteristic polynomial power of that eigenvalue, which was 3, then the minimal polynomial should be the first one. Okay? Because we know that the power of the matrix, here it is 1, the power of the matrix at which we reach the dimension 3 would be the minimal polynomial power, okay, for that eigenvalue. Okay? But here I see that for null space of sigma 1 dimension is 2, and it is not equal to 3, the largest possible dimension. That is why here the characteristic polynomial cannot be this one, because the minimal polynomial cannot be this one, because if this was the minimal polynomial, then the dimension of that null space should have been equal to 3. Okay? So here is what I do. I calculate sigma 1 square. I increase the power by 1. Okay? If I take the square of that matrix, you're going to get this. And I would have 0, 0, 0, 0, and 0, 0, 0, 1. Okay? So this is sigma 1 square. And now I'm going to be looking at dimension of null space of sigma 1 square. Okay? What is the rank of that matrix? The number of linearly independent columns is 1 only. Okay? Only 1 linearly independent column, the rest is 0. Therefore, what is the null space dimension? It has to be equal to 3. So you see that at the power 2, we reach the dimension 3. the characteristic polynomial power. That means that the minimal polynomial power, according to this information, should be 2 for the eigenvalue 1. So this is my minimal polynomial, and this is not my minimal polynomial either. Okay? So what is going to happen when I take the cube of this matrix? The null space is going to sigma 1 cube. What is this dimension? What do you think this dimension has to be? Obviously, since this is the largest dimension that we can reach, this is going to remain as 3. And if I increase the power any further, I would get dimension 3 forever, for all increasing powers. Okay? So for this matrix, actually we have null space of sigma 1, null space of sigma 1 square, and then we have equality, sigma 1 cube, sigma 1 to the 4, etc. Just as an example, let me look at sigma 1 cube. Sigma 1 cube is sigma 1 times that matrix. Sigma 1 times that matrix. If I do that multiplication, you would see that I would get this matrix. Okay? So here that, yes, 0, 0, 0, 1. It's the same matrix, so the null space should be the same. So you see that knowing these null space structures here will give you an idea about what the minimal polynomial powers would be. If you look at the dimensions and if you identify at which power you get the largest dimension, which is the characteristic polynomial power, that power is going to be your minimal polynomial power. So that is the first information that this structure is going to give us is the minimal polynomial powers here. Okay? And we are going to see that when we try to find the Jordan canonical form, the other dimensions will be important as well. Okay? So we are going to see that dimensions of each of these null spaces will uniquely determine the Jordan canonical form of this matrix. And furthermore, this null space structure, we are going to be able to use it in order to be able to find the P matrix that would put the A matrix into its Jordan canonical form. Okay? So this type of structure is going to be important until the end of the course. So in the next lecture, we are going to see how to find the Jordan canonical form of a matrix by looking at these dimensions. All right? Looking at these null space dimensions. And that is going to give us an idea of what is going to happen when we have an A matrix. When we have an A matrix, we are going to directly look at these null space dimension and we will be able to form its Jordan canonical form without actually knowing the P matrix itself. And then next thing is going to be to learn how we can find the P matrix that would bring the matrix into the form of its Jordan canonical form. But that's going to be all for this lecture. It was quite tiring. Thank you for watching. Bye-bye.